The topic of today, deployment strategies for 3D interstellar solar cells. I'm working on this with my PhD supervisor, Professor Martin Theimer, who himself will have a keynote speech today. So yeah, you may join it. And as you can see, or other way, my presentation will be about some new design ways of solar cell topologies and the associated deployment strategies. As you can see in the render, on the right side, there are some substantial changes to the way of how we commonly would create a solar cell. So yeah, let's get into it. So today what I want to show you is how those changes affect our general mission concept and what technical challenges will arise, as well as what we already have achieved in the very early stages of our research. Our roadmap starts with a simple idea. We want to use an alternative cell material than commonly used mylar materials. This leads to the idea that we are not longer bound to two-dimensional geometries for our cell. So with three-dimensional topologies, the structural integrity rises actually, which in return can lead to a reduced total spacecraft mass. This also means that in the future, the size of solar cells might increase in order to generate more thrust and therefore gaining payload mass budget. In the end, we need all those steps to eventually build a spacecraft that could go into interstellar space. Let's start from the beginning. In 2020, a colleague of us, Dr. René Heller from the Max Planck Institute of Solar System Research in Germany, published the idea to use a material called Aerographite to build a light sail to go to Proxima Centauri. Aerographite is a carbon-based material that stands out due to its microscopic and porous network structure, which leads to a very low density, especially for solid materials. This material is currently researched and produced at the Material Science Department at the Technical University of Hamburg. And if we look at the material characteristics and we compare Aerographite to the coated mylar, we see that the density is up to 4 magnitudes lower, actually. On the other hand, Aerographite, as you can see on the picture, it's pitch black. So it only absorbs electromagnetic radiation, so we are not benefiting actually of the reflecting regarding the radiation term of the general thrust equation. So this is one point we carefully have to balance. Mass and therefore cell characteristics against thrust and speed for potential interstellar travel. But there are some other benefits that suit our mission design. Generally speaking, what we want to do is we want to launch a stowed sail and send the whole spacecraft into an orbit around Earth. From there on, we go into a transfer orbit to the Sun. And due to the carbon base of the material, its melting point is quite high and also provides very strong heat insulation. That means we can go very close to the Sun, actually a few million kilometers, to benefit from the radiation. And there we will deploy the sail. And in order to go interstellar, we also, as we always, have to reduce mass. That's the main factor actually. We have to reduce mass, and we can do this by, for example, losing the attitude control system. So we plan on sending a main satellite attached to the sail to basically aim the sail towards the required direction, and then release it, and it starts its journey. At the very point where the satellite holds the sail, we experience higher values of solar radiation pressure and solar wind due to the close vicinity to the Sun, which in fact leads to increased loads on the sail itself. So we started to think about changing the topology of the sail into a three-dimensional, rotationally symmetrical shape, which can absorb those loads more effectively than a two-dimensional. First, we simulated a standard 2D unsupported disk shape of a sail with the preliminary parameters of 3 millimeters of thickness and a diameter of 10 meters. For this, we implemented a material model for the Aerographite, and this model is based on the results of the research results of our colleagues in Hamburg, and will be further developed in the future. What you can see on those figures, it's a 2D sail shape, but with various fixation strategies to the satellite bus. So on the top left, there is a common center fixed sail, as we know it from missions like Light Sail, for example. On the top right, the fixation goes all along the rim. There is a some pop-up, interesting. Okay, let's go on. So on the top right, there is a rim fixation, basically, which holds the sail in place. The bottom left, it's more like a point fixation, you can say. For example, imagine struts going from the sail to the satellite bus. And on the bottom right, there is a combination of center and point fixed. The results we're seeing here are total deformations of the sail itself. And if we take a look into the maximum values, obviously the deformations are ridiculously high, but will cause the sail to break apart. But you can also see an improved deformation behavior with the different fixation strategies. In comparison to the 2D shape, on this slide you can see a hollow semisphere with different amounts of flattening from min to max. And it's interesting that we actually can eliminate basically all deformations by changing the shape to a three-dimensional shape. The main deformation will always develop in the center of the sphere, as seen in the figure on the bottom right. We have a maximum deformation of 7.7 meters. So a 3D topology, of course, increases the mass because we have more material we put in the sail. But this is the before mentioned balance we have to find between thrust and mass. Yeah, so in terms of reducing the mass further, we took a look into the deployment strategies for our sail. So, and especially we took a look into deployment strategies used by ongoing and successful missions of the past. So either the use of booms to deploy the sail, like in the Light Sail 2 mission, or spinning tip masses, like in the Icarus mission, require heavy components that have to stay attached to the sail during the flight. So in case we can find a different strategy to deploy and stabilize the sail during the flight, we can further improve the performance of the Aerographite sail. So as we look at the resources available to us and to be used in the vicinity of the Sun, we can come up with various strategies. On the one hand, we can use the increased amount of electromagnetic radiation. This allows us to work with the shape memory effect of alloys like nitinol. The concept was preliminarily researched and validated actually in combination with a miniature Kapton sail by an Italian team in 2019. So we are interested to see what happens actually in combination with Aerographite instead of Kapton. Yeah, the memory effect can either be activated by an active power supply or by the infrared spectrum of the electromagnetic radiation. Aerographite itself seems to have some interesting material characteristics. This includes its behavior in plasma environments and its electrical behavior, and is, as mentioned before, researched by our colleagues in Hamburg. So, we're looking forward to see what they come up with. So this brings us to the plasma effects. That's what we are doing right now. The idea behind the solar plasma deployment, as you can see, and the Coulomb deployment, is to use equally charged electrodes to distribute it across the sail surface to use the Coulomb forces between them for deployment and stabilization. So for those of you who have never heard of electrodes, here's a short introduction actually. So the name is based on the two words electricity and magnet, so electrode. And as you, electrodes are, as you can say, it's just a charged object that have permanent electrostatic fields comparable to the magnetic field of a permanent magnet. Electrodes are, mostly made of polymers, although any dielectric material can be used. So what is the most important thing? For us, this is actually a completely passive system, so we don't need any active power supply, no power generators, no power distribution. This, of course, again, would reduce the total mass of an aerographite cell. So on the right side, you can see how those the different types of the electrodes, which vary in the way of creating the electric charge. On the top, you see the schematic of the most commonly used surface and space charge electrodes that carry elementary charges to create electric point charges. The third way on the bottom would actually be to create dipole moments inside of the dielectric material. Implementing point charges across the cell surface let the stowed cell experience very high Coulomb forces. So by opening the compartment of the cell, the electrodes will drift apart and pull the cell along, effectively deploying the cell and stabilizing it. After the full deployment, the cell and its payload will detach from the main satellite and start its journey. This also converts the spacecraft basically into a hybrid sail by additionally using those electrodes as an electric sail to surf along the solar wind. So we have not looked into detail how this will work, but we will in the future. As I said, electrodes can be created in various ways. So we did our own research on how to create stable, highly capable, lightweight, and resistant electrodes. So we are currently producing space charge electrodes, but slightly different to the common approach. As you can see in the top figure, our electrodes are built in a sandwich-like structure. So the core is made from a thin metal layer. So far we use copper to trap the elementary charges. And surrounding this are two layers of epoxy resin and Kapton, both with high dielectric strength to build a dielectric sheath around the metal layer. And the bottom left figure, you see the prototypes which have been iterated multiple times to improve the stability of the electrodes. And on the bottom right figure, you can see actually the test setup we used so far, containing the electrode in the center, the probe of an electrostatic voltmeter to measure the surface potential of the electrode, a grounded cage to minimize the measurement errors of the surrounding, and a layer of silica beads to reduce the atmospheric humidity. The whole setup is then covered by a lid. And to charge the metal layer of the electrode, we use a high voltage electrode connected to the extending copper strip you can see on the left side. The electrode then is removed while active, and the strip is covered with epoxy resin to shield the charges from the atmosphere. So what we find, our electrodes actually can hold their charge and potentially can be used for the Coulomb deployment. The diagrams show the surface potential of various electrodes and over various time periods actually. But we have to do further research. As you can see, there are those drops in the beginning of every measurement. We want to know why the surface potential is dropping so far. As we think so far, this is due to atmospheric ionization. So our next step would be actually to get into vacuum and to do and repeat the experiments under vacuum conditions. So this will happen in the next couple of months and hopefully further improve our electrodes and eventually helps us validating the Coulomb deployment strategy. And this brings me to the end of my presentation. Thank you very much for your attention. I think we have some time for some short questions. Otherwise, I'm glad to answer in more detail after the session.